signal to this guy. We know that this is going to have a frequency response of what this is right here, which is a low pass filter. So what we're going to anticipate is, as long as our PWM frequency is higher than that cutoff, what we're going to see on this output voltage is something that's more or less a DC signal, which is essentially the duty cycle percent times RVN from the PWM. Right? So, what are we talking about when we say PWM? So a PWM signal is basically a signal, it's a square wave between 0 and some V, where T, the period, is constant. I have a T on, I have a T off, such that obviously T on plus T off is T. When I look at T on, the T on time, or the percent duty cycle, is the T on time over the total period, which is obviously nothing more than T on over T on plus T off. So you're going to use this percent duty cycle. You're going to generate a duty cycle of some frequency T that I tell you guys to be able to control, where you're going to control T from lab view on a VI, and you're also going to generate or control using a dial on lab view the duty cycle. So far so good? So the way this works, if I have some V, I have percent duty cycle of 50%, let's just suppose this is equal to 10 volts, 50% duty cycle. At 10 volts, obviously is going to produce 5 volts, right? And for a 25% duty cycle at 10 volts is going to produce 2.5 volts. Okay, 75% duty cycle at 10 volts is obviously 7.5. So a first order system is going to actually pull everything else. So remember, the cutoff frequency says anything lower than omega C passes. Anything higher than omega C is removed. That's the idea behind the low pass filter. So this square wave, you guys remember lecture last quarter about PWM? Kind of, sort of, yeah, maybe? I'm going to give it to you again, just to make sure you really understand. But the first order system is going to look like this. And there's going to be a phase component. Oh, you guys, so you guys remember doing Bode plots? Yes. So there's our Bode plot as well, right? So for the lab, you're going to generate this PWM. You're going to apply that PWM to this signal. And what I want you to do is to sweep the frequency of your signal. No, I take that back. Part 1 is build a PWM. Part 2 is to build the circuit using the function generator and the oscilloscope. What you're going to do is start with the frequency of, say, 1 hertz, or probably 1, maybe 10 hertz. What voltage do you get? So here's what we're going to do. We want to put a sinusoid in here of some value f, let's say 100 hertz, where it's a plus minus 1 volt. If the frequency is allowed to pass right here, then we're going to see 1 volt come out, right? So we put in 1 volt, we get out 1 volt. All right, so then we say frequency is, say, 100 hertz. Put in 100 volts, or say 100 hertz at plus minus 1 volt. I get it out, because the question is where is omega C at? And I could do 200 hertz all the way up to, say, I think I tell you in here, let's just suppose for, I say I go up to 200 kilohertz. somewhere in there, this amplitude is going to decrease. The frequency at which that amplitude decreases to 0.707 minus 0.707 is omega c. So I can actually find omega c, and therefore I can find A, which implies, well, because I can find it through tau, because I know tau is omega. Because I know omega c, I can find A, I can find the system's response by sweeping its frequency. So what I'm going to look at is I'm going to find the system response, or the behavioral response of the transfer function that you guys are also going to calculate for this. So you'll calculate the schematic. Later on, for the last part, the analysis part that you're going to do at home, you're going to build this system in Simulink like we covered already. We've talked about how to do that. You're going to implement the G of S. Part 3, once we have a pretty good cutoff frequency, so you know where this needs to be, then you're going to set your PWM frequency here, and you're going to vary the duty cycle such that the duty cycle will come out across here as we would see duty cycle over here times the in to this guy right here. So this is going to be, in part 3, apply the LabVIEW signal that you generated in part 1 to the filter, get the duty cycle out. So far, so good. What this is emulating is a first order system that we talked about literally today in class, and we'll continue to talk about much further next week. First order system is very much the approximate of a thermal system. Very simple one, I might add. So we have some thermal system that's going to respond when we turn it on, and it's going to respond as a function of its transfer function. It's G of S. So there's going to be some G of S right here. So we're going to use this as a G of S just to make a G of S to then try to create a G of S in Simulink. So we want to capture the output when we apply the input. You can capture it on the scope, or if you want to try and capture it on the MyReal, you might be able to. I don't know if it's too fast. If you want to, you can. Somehow you have to capture the response when you apply the input of the duties of the PWM to your plant. Because what we want to do, as you recall last time we spoke, is we're going to have a control system where this is some thermal control system. We want a temp out. We want to feed it back by using a sensor. We want to take our input command or our reference. We want to calculate the error of the output to our input using the sensors, which is the transistors that you guys created the PN junction for, that you're doing tonight. So tonight you're creating this. You're going to figure out how to somehow create a signal, which would be a PWM signal, to make that thermal plant the appropriate temperature. Makes sense so far? How we do that will be by means of a controller. We will talk about the finality of the controller, and we'll talk about what happens when we actually close the loop. So for right now, what we're looking at doing is modeling our sensor, getting an understanding of how our sensor responds, and we're going to figure out how to drive our plant by means of a PWM. Knowing that the PWM gives us a DC value as a function, or a DC value as a function of the duty cycle times the voltage that it's swinging between in the PWM. Make sense? Absolutely. So let me say it again. So what we want to do is, tonight, we're taking a G of S. We're simulating a G of S. I'm just saying it looks like this. What this guy is, you have to find. Some G of S is going to exist. What we plan to do for our control system is we have a plant that we don't know. I said it's going to be some G sub S, or maybe you're going to have to figure out what that G sub S is. But it's going to be a low-pass filter. We're going to use our transistors tonight. We're going to characterize and understand the way those sensors work so that we can then create not just a sensor, but we actually create some kind of an H of S, which relates the output to the input here. Remember, it's got a negative slope, doesn't it? That's what you're going to see. Voltage goes up as the temperature goes down. But here, you're going to have a temperature that's going to be the other way around. So you're going to have to figure out some way of relating the applesauce back to the apples. So this is what our temp sensor is doing. This is what you're making. In addition, you're also experimenting with the accelerometer, because we have to do other sensors. But the thermal control system, we'll understand H of S, and we're going to then figure out how to drive our G of S, which in this case is this guy right here. So right now, this is our simple G of S. Next week, the G of S will actually be something else. It'll be a thermal heater that you guys will also create. But we want to make sure we can do PWM first with a known system that we can just build a simple op-amp. It also turns out that the frequency response of a thermal system is very, very slow. It takes forever to heat up and to cool down. So let's go ahead and start with something that has a little bit better frequency response to understand it. Because what we're talking about is this A will have a better omega C. So here our omega C is going to be way out here, versus the thermal sensor would be over here, closer to a 0, which is a much lower frequency response. Make sense?